China's robots are starting to outperform humans on ice, and that might be only the first sign of a much bigger shift. In just 12 months, the running speed of Chinese humanoid robots jumped by more than 200%. Yes, you heard that correctly, 200% in a single year. That is not the kind of progress people expect from normal technology updates. It is more like comparing an old family car to a high-performance race machine. All within the span of a single year. That level of improvement is enough to make people pay attention. The next 4 stories suggest this may be more than a lucky breakthrough. It could be part of a much larger plan. First, there's the robot that almost seems impossible. Imagine scrolling through your phone late at night when a video suddenly grabs your attention. A sleek white humanoid robot, standing around 4.5 feet tall, glides onto an ice rink wearing skates. Nobody is pushing it and no handler is guiding its movements. Then it moves across the ice with surprising confidence, shifts its balance, and pulls off something that leaves viewers stunned. It lands a front flip on the ice with remarkable control. Human figure skaters often spend years training to develop that kind of precision. At first glance, many people assume the footage must be fake, computer generated, or heavily edited. But the details tell a different story. The natural lighting, the imperfect reflections on the ice, and the small spray of ice chips when it lands make the scene feel strikingly real. This is not a movie scene or a special effects trick, it's real footage. The machine behind it is not some secret military project or an ultra-expensive prototype hidden inside a restricted research facility. It is the Unitree G1, a humanoid robot that is commercially available today. Its price tag is around $17,990, putting it in the same range as many cars people buy every day. But the most surprising part is not the skating, and it is not even the front flip. The real story is how the robot learned to do it. Humans usually learn physical skills through trial and error. Whether it is riding a bike, skating, or mastering a sport, people often spend weeks, months, or even years practicing and improving little by little. This robot followed a very different path. Instead of learning entirely through real-world practice, it was trained inside a virtual physics simulation. There, it could perform countless training attempts at incredible speed, allowing its control systems to improve far faster than traditional methods would allow. Once that training was complete, the updated software could be deployed to other robots of the same model, giving them access to the same learned capabilities almost instantly. That one detail changes the way many people look at a viral skating video. Suddenly, it is not just about a robot performing a cool trick on ice. It raises bigger questions about how quickly robotic abilities can spread and improve. And if this is the kind of performance being shown publicly, the next story begins with something even more eye-opening: a race. The method behind all of this is what really changes the game. Before getting to the race, it is important to understand how that skating performance became possible, because the skating itself is not the biggest breakthrough. The real breakthrough is the training system behind it, and once you understand that process, every story that follows takes on a whole new meaning. The approach is called sim-to-real transfer learning, and the concept is surprisingly straightforward. Instead of placing a robot on real ice and risking countless crashes that could damage expensive hardware, engineers first create a highly detailed virtual version of the real world. This digital environment can simulate gravity, friction, balance, weight distribution, momentum, and other important physical factors with impressive accuracy. Inside that virtual world, the robot can train at incredible speed. It goes through millions of attempts, millions of mistakes, and millions of tiny adjustments. What could take months or even years in the real world can be compressed into just hours of intensive simulation. The system does not simply repeat the same scenario again and again, it constantly changes the conditions. Different ice surfaces, different speeds, different approach angles, and countless other variables are introduced. By facing a wide range of situations during training, the robot becomes better prepared to handle challenges when it eventually operates in the real world. The goal is to force the algorithm to find find solutions that work across many different situations, not just one carefully controlled test. By the time the software is transferred to a physical robot, it may have already been exposed to more unusual scenarios and unexpected challenges than a human athlete could encounter during years of training. That is a huge shift in how skills can be developed and improved. Think about it this way. A person spends years learning how to drive, building experience 1 hour at a time. Those lessons stay inside that person's mind and cannot simply be copied to everyone else. If another person wants the same level of skill, they have to go through their own learning process. Robots operate under a very different model. Once a useful capability is developed and refined, that software can be distributed across other robots using the same platform, allowing improvements to spread much faster. That is what makes sim-to-real training so powerful. The learning can scale even when the hardware stays the same, and this approach is not limited to eye-catching demonstrations on an ice rink. Robotics companies in China and elsewhere are using similar methods to train machines for a wide variety of physical tasks. Walking across uneven terrain, climbing stairs, handling oddly shaped objects, and moving through crowded environments can all be practiced in simulation first. Millions of virtual attempts can be used to refine performance before those lessons are applied in the real world. The skating video may be the most dramatic example people have seen, but it is only one illustration of how rapidly robotic training methods are advancing. While millions of people were focused on a robot landing a front flip on ice, another Chinese robot was attracting attention for a completely different reason. This time the headlines were not about flashy tricks or viral videos. They were about a performance that made many robotics experts take a second look at the numbers because the results seemed almost unbelievable. The event took place in Beijing in April 2025. It was a half marathon covering 13.1 miles of real roads under real outdoor conditions. There were no special shortcuts, no controlled laboratory environment, and no smooth indoor testing surface. Among the participants were humanoid robots competing alongside human runners on the same course and under the same event conditions. One robot known as Honors Lightning reportedly crossed the finish line in 50 minutes and 26 seconds. That time immediately sparked discussion throughout the robotics community. For comparison, the human half marathon world record has been set by athletes operating at the highest levels of human endurance and training. Seeing a humanoid robot post a result that appeared to challenge or surpass benchmark human performances caught the attention of engineers, researchers, and technology watchers around the world. Whether viewed as a milestone or a glimpse of what may come next, the result added another dramatic chapter to the rapidly evolving story of advanced robotics. A robot posting an impressive race time is already enough to grab attention, but the bigger story is the speed of improvement behind it. The result was remarkable on its own. Yet many observers were even more surprised when they looked at where humanoid robots were just 1 year earlier. According to reports discussed in the robotics community, some Chinese humanoid robots were completing similar long-distance runs in roughly 2 hours and 40 minutes only a year before. Then, within a single development cycle, performance improved dramatically. That kind of jump is what sparked so much discussion among engineers and technology analysts around the world. This was not the sort of gradual progress people usually associate with small software updates or minor hardware adjustments. Instead, it highlighted how quickly robotic systems can advance when improvements in software, training methods, sensors, and mechanical design all come together at the same time. The pace of development suggested that researchers were still far from reaching the limits of what these machines might eventually achieve. To put the change into perspective, imagine a runner who finishes a half marathon well behind elite competitors 1 year, then returns the next year performing at a completely different level. That comparison helps explain why the reported progress in Chinese robotics drew so much attention. It was not just the final result that stood out, it was the speed of the improvement itself that made headlines. To understand what happened, it is important to stay focused on the full picture. Not everything went perfectly during the race, and accuracy matters here. Several robots experienced problems along the course. Some lost balance, some encountered technical issues, and others required assistance from their support teams. Reports indicated that only about 38% of the competing robots completed the event fully autonomously without human intervention. That reality has fueled debate among robotics experts. Rodney Brooks, The MIT roboticist, known for his major contributions to mobile robotics, has often been cautious about the excitement surrounding humanoid robots. Looking at events like these, he has argued that public demonstrations can sometimes function more as publicity showcases than evidence of real-world deployment readiness. Many experts agree that there is still a significant gap between a controlled demonstration and widespread practical use. At the same time, the bigger question is not whether the robots perform flawlessly, it is how quickly they are improving. Technology development is rarely a straight line. Early versions often struggle, make mistakes, and reveal weaknesses. What matters is the direction of progress and how fast those weaknesses are being addressed. When robots fail during events like this, engineers collect the data, analyze what went wrong, and feed that information back into their development systems. The next generation is then trained using those lessons, allowing researchers to improve performance and reliability over time. That cycle of testing, learning, and refining is one reason the field is advancing so quickly. And the marathon was about much more than running speed. The event tested endurance, balance on changing surfaces, power efficiency, and the ability to operate for extended periods under real-world conditions. Those same capabilities are important for tasks in factories, warehouses, research facilities, and other environments where robots must function reliably for long periods without constant supervision. That is why many experts viewed the race as more than a sporting event. It was also a large-scale technology demonstration with broader implications for the future of robotics. If the marathon demonstrated endurance and long-term performance, the next project focused on a very different challenge entirely. The goal was not simply to see how far robots could travel, it was to push their balance, coordination, recovery systems, and physical control to the limit under intense conditions. In February 2026, Shenzhen, China became the center of attention when what was described as the world's first humanoid robot combat league officially launched. The event featured a championship prize reportedly valued at $1.4 million, drawing significant interest from robotics enthusiasts, engineers, media outlets, and technology observers around the world. What surprised many people was how closely the competition resembled a professional sports league. There were tournament brackets, head-to-head matches, spectators, cameras, and championship titles. Rather than being presented as a traditional research demonstration, the event was designed as a public competition that showcased advanced robotic capabilities in a highly visible way. The robots participating were reported to be Engine AIT 800 units. Inside the arena, they demonstrated fast movements, balanced recovery, and coordinated physical actions that were far beyond what many people associate with older generations of robots. Viewers watched machines perform complex maneuvers, maintain stability after impacts, and quickly regain control after being pushed off balance. The result looked dramatically different from the slow, awkward robot demonstrations many people remember from the past. But the most important part was not the spectacle itself, it was the engineering purpose behind it. According to statements from organizers and developers, competitions like these generate large amounts of performance data that can be used to improve robotic systems. Fast-paced physical challenges help expose weaknesses in balance, motion control, reaction systems, and hardware durability, giving engineers valuable information for future development. Developers involved with the project reportedly stated that this type of testing could accelerate development cycles by as much as 30%. In other words, the competition was not just entertainment, it was also being used as a practical tool for refining the next generation of robotic technology. That combination of public spectacle and real-world engineering objectives is what made the event stand out in the global robotics conversation. According to the organizers, the goal was not simply to create an event that attracts attention. Their public statements emphasize something much more practical. They believe these competitions can significantly speed up development. Rather than describing it as an experiment or a possibility, developers pointed to measurable improvements in testing efficiency and system refinement. When you think about it, the reasoning is straightforward. High-intensity physical challenges expose weaknesses quickly. During a short match, engineers can observe how a robot responds to sudden impacts, balance disruptions, rapid changes in movement, and unexpected conditions. That creates a large amount of valuable performance data in a very short period of time. A single bout can test multiple systems at once, including dynamic balance, motion control, recovery behavior, structural durability, and the ability to react quickly after losing stability. These are not skills that matter only inside a competition arena. Similar capabilities are important in many real-world environments where robots may encounter obstacles, uneven surfaces, accidental collisions, or changing conditions. For example, a robot that can regain balance after being pushed may also be better equipped to recover from unexpected contact in a busy workplace. A machine capable of maintaining stability during complex movements may also perform more effectively when navigating difficult terrain or crowded spaces. From an engineering perspective, the competition becomes a fast way to identify weaknesses and improve performance. This approach also highlights a broader difference in development styles that observers often discuss. Some robotics programs focus on highly controlled methodical progress with carefully documented public demonstrations. Others emphasize rapid testing, frequent iteration, and collecting large amounts of real-world performance data as quickly as possible. Both approaches aim to improve robotic systems, but they often move at very different speeds and follow very different development philosophies. Consider the range of abilities being tested in these robotics events. Different challenges place very different demands on a machine. Some require speed and agility, while others focus on balance, coordination, endurance, recovery, and rapid decision-making. Excelling across multiple categories is far more difficult than mastering a single specialized task. That is why many observers paid close attention to the variety of disciplines included in these competitions. The key question was not whether a robot could perform one impressive action. The bigger question was whether modern humanoid robots are becoming increasingly capable across a wide range of physical challenges. That broader versatility is what researchers and engineers are ultimately trying to achieve. There is also an international dimension that attracted attention. Reports indicated that teams and participants from numerous countries were involved, while China served as the organizer and host. As the host nation, it played a major role in establishing the competition structure, event formats, judging standards, and performance benchmarks used throughout the event. That matters because the organizations that create major competitions often influence how success is measured. When a new international event becomes widely recognized, its standards can shape how future performances are evaluated and compared. As a result, some analysts see these robotics competitions as more than technical showcases. They may also help define future expectations for the industry. Another detail stood out to many observers. Before one event had even fully concluded, organizers had already confirmed plans for the next edition in August 2026. That announcement signaled a long-term commitment rather than a one-time demonstration, designed only to generate headlines. The significance of that decision goes beyond a single tournament. Repeated annual events create an ongoing platform where progress can be measured year after year. They allow researchers, companies, and countries to showcase improvements, compare results, and establish new performance milestones. In that sense, these competitions are becoming more than isolated exhibitions. They are evolving into recurring international benchmarks for humanoid robotics. And with China already drawing attention for the rapid pace of its robotics advancements, many people will be watching closely to see how much further the technology progresses before the next competition takes place. All of this leads to a bigger question. How did China become such a major force in humanoid robotics in such a short period of time? The answer, according to many industry observers, goes beyond talent or technology alone. It also involves large-scale investment, long-term planning, and a coordinated effort to accelerate development across the robotics sector. This is the part that often gets overlooked when viral videos dominate the conversation. A robot skating on ice grabs attention. A robot posting an impressive race result creates headlines. But behind those moments is a much larger system of funding, research, manufacturing, and competition that operates on a national scale. Reports have highlighted billions of dollars in investment flowing into robotics development, with a large number of companies working on different approaches at the same time. Instead of relying on a single organization to drive progress, multiple firms, research groups, and technology teams are pursuing their own solutions simultaneously. That creates a highly competitive environment where new ideas can be tested, improved, and scaled quickly. Supporters of this approach argue that it offers a different model from traditional venture capital systems. Venture capital often focuses resources on a smaller number of companies that appear most promising. A broader investment strategy, by contrast, allows many projects to move forward at once, even if some efforts fall short of expectations, successful projects can still produce major advances for the industry as a whole. Another factor frequently mentioned by analysts is the role of long-term national planning. Chinese policy documents and development plans have identified advanced technologies, including robotics, as strategically important sectors for future economic and technological growth. That level of focus can help align investment, research, manufacturing, and workforce development towards shared goals. When viewed together, these elements help explain why the rapid progress seen in robotics is not being treated as a series of isolated breakthroughs. For many observers, it looks more like part of a much larger effort to build long-term leadership in one of the world's fastest-moving technologies. When a government identifies a technology as strategically important, the effects can extend far beyond a single industry. Research institutions may increase funding in that area, universities may expand related programs, manufacturers may invest in new production capabilities, and businesses may look for ways to adopt the technology more quickly. Over time, those efforts can create a powerful ecosystem that supports rapid development. Some market research groups have pointed to the growing presence of Chinese robotics companies in commercial deployments. According to certain industry reports, several Chinese firms have emerged as leading suppliers of humanoid robots designed for practical business applications. The key point is that attention is increasingly shifting away from laboratory demonstrations and toward machines performing useful tasks in real-world environments. However, before concluding that the race is already over, it is important to consider the perspective of some of the field's most respected critics. One of the most frequently cited voices is Rodney Brooks, a robotics pioneer whose work has had a major influence on modern mobile robotics. Brooks co-founded iRobot, contributed significantly to robotics research at MIT, and has spent decades studying how robots perform outside carefully controlled environments. Brooks has often expressed skepticism about the excitement surrounding humanoid robots, and he has described some highly publicized robotics events as publicity-focused demonstrations rather than clear evidence of widespread deployment readiness. His viewpoint carries weight because it comes from deep experience rather than headlines or social media trends. There is evidence supporting some of his concerns. Looking back at major robotics competitions, the results were impressive but far from perfect. During the Beijing half marathon, for example, only a portion of the participating robots reportedly completed the course fully autonomously. Others experienced difficulties that required assistance, highlighting how challenging real-world conditions remain for current robotic systems. That distinction matters. A robot performing an impressive task during a controlled demonstration is not necessarily the same as a robot operating reliably for long periods in unpredictable environments. Real workplaces introduce constantly changing conditions, unexpected obstacles, varying lighting, equipment interactions, and countless other challenges that are difficult to reproduce perfectly during testing. And this is where the debate becomes especially interesting. Supporters see rapid improvement, record-setting performances, and accelerating development cycles. Skeptics see systems that still face major reliability challenges outside demonstration settings. Both observations can be true at the same time. The central question is no longer whether humanoid robots can perform remarkable feats. They clearly can. The bigger question is how quickly those impressive demonstrations can be transformed into dependable machines that operate day after day in the real world with minimal supervision. That is the challenge researchers everywhere are still working to solve, and it may ultimately determine who leads the next era of robotics. Many experts agree on one important point: humanoid robots have not yet reached the stage where they are replacing human workers on a massive scale across every industry. Claims that the technology has already solved all of its major challenges often go further than the available evidence supports. That is one reason voices like Rodney Brooks continue to attract attention. His skepticism serves as a reminder that impressive demonstrations and reliable large-scale deployment are not the same thing. Brooks and other critics argue that current systems still face significant limitations in real-world environments. Looking at today's technology, that perspective has strong support. However, the discussion becomes more complicated when people shift their focus from current capabilities to the rate of progress itself. For many observers, the central question is not simply where robotics stands today, it is how quickly the field is advancing. Several factors frequently appear in these discussions: the pace of improvement, the scale of investment flowing into development, and the growing use of advanced training methods such as sim-to-real learning. Take the improvement trend as an example. Reports showing dramatic performance gains over relatively short periods have drawn attention because they appear much faster than the gradual progress people often expect from traditional engineering cycles. When improvements happen repeatedly and build on previous gains, analysts sometimes describe the process as a compounding effect rather than a purely linear one. Another important factor is how failures are treated. In modern robotics development, mistakes are often viewed as valuable data rather than setbacks. When a robot encounters a problem during testing, engineers can analyze exactly what happened, update training systems, and use those lessons to improve future versions. As a result, weaknesses discovered in one generation may help strengthen the next generation much more quickly than in the past. Investment scale also plays a major role in the conversation. Around the world, leading robotics companies continue to produce impressive machines capable of increasingly advanced movements and tasks. Firms such as Boston Dynamics have demonstrated extraordinary achievements in mobility and control. At the same time, other countries and organizations are investing heavily in their own approaches, creating an environment where multiple development strategies are competing and evolving at once. That combination of rapid iteration, large-scale investment, and increasingly sophisticated training methods is why the future of robotics remains one of the most closely watched technology stories in the world today. Supporters of different robotics programs often point to companies such as Figure AI, Boston Dynamics, and other major innovators that are working toward real-world deployment of advanced humanoid robots. These organizations have achieved impressive results and continue pushing the technology forward. At the same time, many analysts note that different regions are approaching the challenge with very different levels of investment, organizational structures, and development strategies. One argument frequently raised is that large-scale programs can run many research efforts simultaneously rather than focusing on only a few projects at a time. When dozens or even hundreds of teams explore different solutions, the chances of discovering unexpected breakthroughs may increase. More experiments can generate more data, reveal more weaknesses, and uncover new approaches that might otherwise take years to identify. This is where the discussion often returns to sim to real training, the same concept highlighted by the skating demonstration. Many researchers view this as one of the most important advances in modern robotics because it allows robots to learn and refine behaviors inside detailed virtual environments before applying those lessons in the real world. The advantage is not simply speed, it is scale. Instead of relying entirely on physical testing, engineers can run enormous numbers of simulated training sessions, exposing robots to a wide variety of situations and challenges. Once improvements are validated, updated software can be deployed across compatible systems far more efficiently than retraining each robot individually. Because of this, some experts argue that software and algorithms may become just as important as hardware in determining future progress. A major improvement in a robot's control system can potentially benefit many machines at once, allowing capabilities to spread much faster than in traditional development models. This dynamic does not always show up when comparing robots at a single moment in time. What often attracts attention is the possibility that today's improvements could accelerate future improvements, creating a cycle of increasingly rapid advancement. That is one reason events such as skating demonstrations, robotics competitions, endurance races, and international showcases receive so much attention. They provide visible snapshots of how quickly the technology is evolving. Whether one agrees with the most optimistic predictions or the most cautious assessments, there is little doubt that humanoid robotics has advanced dramatically over the past decade. The debate now centers less on whether progress is happening and more on how far and how fast that progress will continue in the years ahead. The robots are not perfect, and the skeptics are not wrong to point out the limitations. Current humanoid robots still face challenges, and there is plenty of work left to do before they can handle every real-world situation reliably. But for many analysts, perfection was never the most important benchmark. The bigger question is whether rapid improvement, large-scale investment, and advanced training methods like sim-to-real learning are combining to create a long-term advantage that becomes stronger over time. That is the trend many people are watching closely. Every skating demonstration, every endurance race, every robotics competition, and every international showcase adds another piece to the picture. What makes the discussion so fascinating is that future leadership does not depend on robots being flawless today. It depends on how quickly they continue to improve. If one ecosystem consistently develops faster, learns faster, and deploys new capabilities faster, the gap can change dramatically in just a few years. That is part of why the Unitree G1 attracted so much attention online. It was not only because people saw a robot skating with impressive control, it was because the performance symbolized something bigger. A machine priced within reach of commercial buyers was demonstrating capabilities that would have seemed unbelievable only a short time ago. For many viewers, that viral moment felt like more than a stunt. It felt like a glimpse of a technology moving forward at remarkable speed. And whether people see that as exciting, disruptive, or both, one thing is clear: the pace of progress is accelerating, and the world is paying attention. Don't forget to like, share, and subscribe for more.